Hello, everybody. Welcome to this very special webinar that we have organized for you. My name is Jonathan Asher, and I'm a part of the CATIA organizations from Dassault Systems. I'm very, very happy to be here with you today with our special guest from Zaha Hadid Architects, Kaloyan Erevinov. He's an associate at the Hong Kong office for Zaha Hadid Architects, and you've seen recently a B1M video that was released on the work that they've done on the Henderson Tower in central Hong Kong. And we have this special guest is going to give us a unique insight into how CATIA was used for that project. A quick refresher, our solutions for CATIA construction span multiple industries, multiple segments, buildings and infrastructure. Today, we get to focus in on the buildings sector, which is very exciting. And without further ado, I'm going to hand it over to our special guest, Kaloyan, to present in more detail the Henderson project and how CATIA was used to design and refine that tower project in Hong Kong. So thank you so much for being with us today. And we'll hand you the screen now, and you can walk us through your exceptional work.
Thank you, Jonathan. So, quick overview of the tower. Here is the combined BIM model that we have, which grew over time. The actual design model is in this section, which is the master model. And over time, due to coordination, we had to import more and more models from other consultants and contractors. So this is the overview of, we had to do facade package, which was primarily done in CATIA. And this is what I'm gonna walk you through shortly today. We have some other bits and pieces, which hopefully we'll have time to touch on. So the way this was developed, it's a little bit, it's not like the traditional convention way of modeling where we have design surfaces made with other software, and usually either consultants or contractors jump in to develop and rationalize it. Due to the nature of the project, actually. So let me switch off some parts, starting with the setting out, because it's a fairly small site. It's about like 50 by 50 meters. And as we want the design with the curved facade, we had to make it buildable, right? We had a very early on engagement with the glass fabricators to get the actual limitations of the glass geometry that it can be built. So this was every single panel has to have a single curvature because it's a tempered glass. So to achieve this thing, because of the small size of the project, basically every time you change the panelization, it changes the outline, respectively changes the GFA. So the way we could control this thing in a quite precise way, it's building up the whole set out very precisely and controllably. So what you can see here, this is the main outline of the facade with the so-called recess, because we have to control the size there as well. And how to say, it's like very important or basic for this thing was the CATIA sketcher, right? Because, and it's the plan set out. So if I enter the sketch, we took full advantage of all these constraints which CATIA provides, right? So basically we have very few straight pieces where we have the openable windows. So they have to be flat, but the rest is assembly of arcs, which are always have to change curvature and tangency, respectively, where the panelization is. And you can see here, so it's basically very precise control and taking advantage of the software constraints to actually fix the geometry in the way that it works. Same for the other one. Of course, we had all the levels, which is more or less nothing that special. It's construction like concrete slab levels, the stack joints of the facade, which were moving in up and down a little bit, so the levels are parametrically tight, and respectively in the very early ages. I mean, now it's all fixed, but the very early ages, whenever we change, this propagates automatically through the model, right? So starting from here, this is basically the basic outlines which control the whole shape of the building. Then we jump actually to the actual facade envelope, right? So here, if I open the model, it was, okay, panelization later on. The way it was constructed as well has to be also, okay, let me switch it back to levels. It has to be constructed in a way that the design surface has also to follow the same rules, right? So basically, single curvature and changes of the curvature only at the stack joint levels, right? So this was just for maybe this one, just for a quick show how this thing was built. As you can see, so this is based on the outlines, which are linked, of course, right? Which are linked from the driver. And based on this, it's all the surfaces are constructed, right? With more or less more like car design in a way, because we have to make sure that all the surfaces are clean and all the tangencies are kept and following throughout, right? So this was, so basically that's how the whole design envelope was constructed. We have 6 bays overall, so the whole building is divided. We call it like A, B, C, D, E. Backside is quite simple. They're the only part where we have like a flat, because that's where the core, the actual core inside of the building is. And the front ones are kind of symmetrical in plan, but they are actually a little bit changing throughout the elevation. But the setouts are the same, and this allowed us to, for example, if we switch on this one, same thing, right? It's like the whole setouts, precise construction lines, allowing for continuous tangent surface construction, which are precisely controlled. I mean, these are always, this is pure cylinder, this is spherical surface, this is translational surface, and so on. Here, these are actually twisted. It's a single curved surface. We have to make sure that all the verticals are straight lines as well. So this was more or less the design process, or the modeling process, so to say, of the main design surfaces. And then we had to keep on checking this all the time, right? So, which was using the very good analysis toolset in CATIA. Specifically here is the, let me see, yeah. For example, we had to always check the whole curvature, if it's, what are the deviations, and if there are any bumps, and so on. So here is, for example, cutting plane analysis, which can be adjusted. Then we had some, okay, so it's more details. This is already where the division lines are. So checking on the division lines, like the panelization lines, to make sure that, as you can see, we have like constant curvature per module, so to say, and the curvature change is happening only where the mullion lines are. So this was designed for the main tower, so to say. I mean, the missing floors, they are here. They just are, here we have a MEP floor, and here we have like a refuge floor, which were a little bit, let's say, okay, give me 1 second. Yeah, there also, everything is respectively divided by base and zones. You can see it's like zone C is the first part, then zone, 10 is the first part, 20 is the first MEP floor, and so forth and so on, right? I mean, the whole thing is throughout the whole tower, this system. And these two floors are in separate model. I mean, from here, they are linked then to another model, because which requires a little bit more articulation, so to say. So, for example, if I switch off, you can see we had the, because basically there are some open area requirements, right? And structurally, we couldn't achieve like the full, I forgot how many percent was. So the airflow was enhanced. These are not only design solution, but these are also technical. We have to have this curved area at the back to enhance the airflow. Here is for the refuge floor, and respectively on the MEP floors. Of course, these are blocked visually by decorative louvers at the front. As you can see, this is already getting into a complex geometry, which was, of course, here is all automated. These are basically either power copies or UDFs run through the whole facade, the whole floor, and of course, this adaptively, keeping the same principle, adaptively constructs the geometry according to every single condition, right? So which was allowed us to have a really precise control. If we open the model, we did, of course, always, but this might take a while, was always taking, we were always have to control the actual open area, which would have been a little bit more challenging if you have to do in elevations, because these are curved areas. It's very hard to do precisely in elevation. So here we had actually in every power copy calculates respectively also the open area, the closed area, and the percentage. So of course we have the inputs, which are linked from the main files. And here, for example, yeah, you see it's like every single louver. Just surfaces which are published, and then you have actually calculation of the open area and of the open ratio. Now I remember we had to achieve somewhere about like just 45%, which we managed to do. So this is for the mechanical floor, which are separated, and then this is for the upper floors, where again, same thing, right? For example, take this louver, calculates automatically the whole open area and the open ratio. So then further on, I'll keep on concentrating first on the tower, and then I will touch on the other parts. So the other challenge, of course, was because of the Hong Kong weather, specifically high wind loads, the whole tower facade is actually unitized system throughout, like from top to bottom. And so respectively, to have this, so we had to then, we went further to actually modeling every single unit, right? So to be, again, this is already glass units with the actual dimensions, right? This is the joint width after calculating for the facade consultants and engineers. Then here we have the openable windows, which are on the flat part. And again, we had to have control to be sure that these are actually all up to parameters, right? So so here we have like every single glass unit throughout the tower modeled, and these were done. You can see here it's like two parts actually, because the first round, which was like quite a few years ago already, this was done with scripting. Again, it's a UDF, which runs through here. You have, of course, you can see the inputs, right, which are basically the whole set out deliver linked from the design file. And so then we had to populate every single unit, UDF, which actually again takes all the basic dimensions, which is like all the corners, and particularly the limitation for the glass furnace was the so-called arc height, which means geometrically the depth of the whole panel, if it can fit in the furnace or not. As I said, yeah, so initially, as I said, this was done by scripts. And then later on, actually, I redid some of them through the component specification, which is found to be quite useful feature, and I'll touch why in a bit. But so basically, well, it's the same thing, right? So basically, every single panel, as you can see here, for example, or let's take some of the curved ones. So these are UDFs, which are populated for the whole tower, and each panel automatically calculates panel area, the four edges, the arc height, and respectively the joint widths are linked to a parameter as well. So in case something changes due to some calculations or something, this is automatically updatable. And all these were then per bay extracted into, here's some basic parameters, extracted into Excel timesheets, right? So that we have them given to the consultants, but also that we can quickly check all the data. Yeah. So you can see here, this is basically every panel, the name and the user feature, respectively area, all the edges, and then the arc heights, right, which were critical for the curved panels. So these are all spit out, right, and can be exported and have an overview and control of the whole of each and every panel. So back to the advantage now of the component specification is basically which allowed me with one set out. So these are the UDFs for this model, just for which are for the dimensional control. Then I could linking another UDF, which are actually in the change of LOD. We can spit out respectively as a separate part, all in much more detail. So for example, if we can see here, these are already much more detailed modeled units, right? This is the whole unitized unit, which is with the glass assembly. We have 4 ply of glass. and respectively the mullions, transoms, and so on, which are again generated for every single case, regardless if it's a flat, cylindrical, or double curved surface. The particular challenge being like unitized, fully unitized system is that because of the interlocking of the units, which were requiring that quite a few, especially in the double curved area, that the aluminum profiles need to be either curved in two directions, which, okay, it's challenging, but still easier because basically they can be rolled in one direction and consecutively rolled in the other direction. But for some areas, this required that the profiles are twisting, which is already a big headache for most of the facade contractors. So we did a study as well, like how much we can actually allow the profiles to be only curved or straight without twisting, and how much this would respectively block the engagement of the units. And so this is the detailed model, which actually inside the model there are two options for twisting or non-twisting profile. You can see here the two different colors, which I linked into a design table, and then this would automatically update. So here we have actually the other units as well, right? And I'm gonna jump to a video because it's a massive model. Takes some time to run this. So the video, of course, is sped up, but just to give you an impression of basically how it goes. So this is the same model. These are the set outs. And then we can actually just expose the higher definition, the higher LOD units. And you can see here, this is the option, the ideal option where the mullions needs to be twisting. However, it is a fabrication challenge, mostly about controlling the accuracy of the outcome. And so these were the options which are non-twisting. And you can see, of course, this is one of the most twisted parts of the building, but you can see how much already they deviate, right? Okay, so I'm gonna jump on another video. So basically, same thing, which allowed us, this is already more detailed view of the same model. And then the way it was constructed, so basically, because at this stage, we don't really need to model precise extrusion, like with all the holes and everything inside. For us, is more about the dimensional control and the actual engagement. So here is a study of the transom and the way it was modeled. So basically the sketch for the transom and mullion are based in the main file, right? In the working file. That means changing or adopting the sketch will propagate and automatically update the detail model. And here, for example, is a short study of the alignment of the pegs of the transom and how they should be located and how this affects the engagement of the unitized panels. Yeah, so this is the sketch. And these were the setouts of the dimensional setouts, like the colored dotted lines are just the basic setout of the distance between the pegs of the transoms and the mullions. So yeah, basically updating it runs through the whole model. Okay, back to the design model. So this is more or less about the tower. Okay, you can switch off the... Right, so apart from the tower part, we have top and bottom of the building, of course, right? So quickly show about the, okay, just for context, right? So at the bottom part, the first 3 floors is a little bit more special conditions because this is where the tower meets the ground. And we have from inner side, it's, so this is no longer unitized system. So this is a double height is actually entrance lobby. So all these panels are supported on a stick system, which are these like solid steel profiles, right? So the limitations, the fabrication limitations of the glass here are a little bit different because these are same height. Every panel is 5 meters height, but the so-called underslang panels are much smaller. So there, the limitation was no longer the size because the size was doable. Then the limitation was the actual radius or the curvature, which again, I mean, this went few iterations. The model is too advanced, unfortunately, to run updates right now. It will take quite a while, but just to show you, so basically the way we were controlling it. Okay. So we had curvature analysis, which actually allowed for basically this gives the minimum maximum radius of the whole glass surface, and on top of this allows like for real-time feedback. I mean, you see it's like just walking, like if there are concerns of any part of the surface, this would actually give you the actual radius, right? So we had to make sure that all this is in the specified parameters, so there's like all of this can be fabricated. And this is mostly about the glass. Of course, there were some challenging metal works as well, like how the column cladding interfaces with the facade. So these are we have actually only 6 columns throughout the whole building. The rest is taken by the concrete core, but they are penetrating the envelope, right? So I'm not sure that this was, so basically here we had to, the way this thing is modeled is actually everything is, it's not really double curve, right? So basically the column is flat and cylindrical, which has to hit exactly another metal, which is like the matching cylinder as well, right? So I mean, with other software, this would take quite a while to match. And here, I'm not sure I can remember the, oh yeah, okay. But it was basically, it's a, sorry. I don't know why I'm, yeah. It was basically a quite challenging geometrical task, but we managed to do it, right? So this is to make sure that then the actual tolerances and clearances are actually constant, right? So there is no like guessing that actually is accurate. And we had as a base, we had like various stages, steel structures from consultant and contractors, which yes, okay, which was mostly done through steel was done by them in Tekla, so transfer was kind of fairly smooth through IFC import, right? But so here we could actually been able to check while modeling and make sure that these complex geometries are meeting the tolerances and clearances, right? And there is no room or any option for clash. So this was for the podium of the tower. And then, okay, the very top, oops, sorry. Oh yeah, so it's another model just for studying, which I missed before. So these are basically all the interior sides of the tower cladding for basically our visual assessment, right? So we have kind of this kind of a curved spandrel panel. Again, everything is either power copied or UDF, because there is also shading there. So basically we also always had to check, so this is curved, but the actual opening for the shading is always a straight line, right? So it was a challenging geometrically because you have to make sure that there are no potential clashes and that it works throughout, right, everywhere. So anyway, just to give you a kind of a taste of the tower top. Tower top is glass-wise is more simple. We managed to engineer this together with ELC. These are about like 8-meter tall glass panels. No fins or anything. So these are basically just supported top and bottom and constrained by the size. And then this all is let me switch out the tower below. It's a glass glazed basically space. These are glass panels which are again made sure they're rationalized. So these are actually all cylinders. There is no double curve here. So these are again generated, checked of course for the angles and so on and so forth. The rest is a metal cladding, which nothing that much challenging. This is all cylindrical glass. And then for, I believe this is more or less, yeah, we have a bit of a perforated panels on the top. But I believe this is not that much. So based, apart from the facade, so this more or less wraps up the set out of the facade. So the model got updated. This was issued for tender. Yeah, we had the local consultant who did, based on our design model, they developed LOD 350, all the systems for the facade tender. Of course, in the process, there were still few changes, modifications, which we've been tracking with the model. But apart from this, we also had like some of the more challenging interiors, particularly interiors that are in direct interface with the facade, right? So these are also all of them constructed together in CATIA. Here, for example, you can see we have this massive steel beams, and to make sure that all of these geometries are matching, respectively, the interior cladding is modeled to match as well. What else can be interesting? Same thing. Okay. The same thing for the entrance, the main entrance. We have two actually entrance lobbies. So the ground level. Oh yeah, of course. Yes, of course. Apart from the whole facade, also we had to make sure that the podium, so-called the ground level, is also coordinated and matching. So these are all the levels of the hardscape to make sure that the falls are okay, correct, and that they interact with the facade properly, right? So then these are the main entrance lobby, which are the interiors, of course, because they are in close interface with the facade. So these are all coordinated and modeled together. And some other for example, here we have, apart from this, we have a footbridge, which is connected to the network of walkways around in Central, in Hong Kong. So the pedestrian access is actually from the bridge level and comes to, let me see if I can find the right model. Comes to another lobby. Let me see if this is readable. So of course, like core, like details, like parts like this, which are either in direct interface to the facades or are requiring like very precise geometrical modeling, were done in CATIA as well, right? So this is, for example, because it's very tight, these are the escalators coming up. So, and then this is the interior lobby where we have some double curved glazing as well with some metal. Then the actual footbridge was very challenging as well because very extremely tight allowances. Just because of the Hong Kong regulations, the whole site coverage and area, and then we have passage widths and so on. So actually the whole, it's a stainless steel clad outside, aluminum clad from inside, but the whole thickness of the walls, which is interior cladding, exterior cladding, plus the structure carrying the roof, is only 250 millimeters. And various restrictions, we have like passage height, vehicle passage height at the bottom, and then we have the actual building at the top, right? So this was very challenging and require, I mean, this is the result of this complex geometry. It's not like that we went for this complex geometry just by itself. It was needed to be able to fit in. And like here, for example, probably can come in handy. Yeah, so these are the coordination with the OC, Eckersley O'Callaghan, who were actually then, like, if you see, this is the whole structure, steel structure, very, very tightly coordinated and with extremely tight allowances. Like if you, so basically the shape again has to be modeled to be, more like a product design or a car design. So we have to make sure that all the surfaces are continuously tangent and smooth, fabricatable as well, right? So this like the radius turning, so, and that the allowances are actually sufficient for the structure and subframe and so on. And so yeah, this is more or less about this. Yeah, right now what we are currently working on is still in progress, and there's like the small, again, just for context, right? So there is a small park next to it, which comes later on. But again, same thing. I mean, this is all actually stone, which is milled, 3D milled in the factory in China. So forth is coming quite nice, but also requires like very, very precise geometrical modeling, right? So to make sure that all this curvature is really nice and smooth. And also, same thing, the whole set out is, again, for example, let me see if I can find the right. Now, as you can see, it's a fairly complex set out. Again, there's a number of let's say passage width and so forth, like dimensional constraints. Here we have, for example, existing tree. So again, like this is really helpful capabilities. We have majorities, like of course arcs, which again have to make sure that they are all the setouts, like clearances, distances are constant throughout, and still produce a very smooth and continuous curvature. And what helps us also control now is like in the terrain, we have also the contour map, so we can make sure that control constantly like the falls and basically the geometry, the slopes of the paving, for example. So here, make sure that like the water runs in the right direction, and they are compliant with all the various regulations here in Hong Kong, right? For so that it's not too steep or doesn't hold water, and of course helping for the landscape, like the soil levels and so forth and so on. Another thing which might be interesting is now very in the late construction stage, for example, we had, for example, there is like one small kind of a special staircase, which was done here again, because of course here in Hong Kong is like very, very challenging and very restrictive. Maybe just for context where it is. It's like on the fifth floor of the building. On one side is like connection of the public level to our upper floor. Was done here because it's a solid surface, but it's almost no tolerances left to the steel structure, which again was developed together with, okay. yeah, just to give you context. So this is like very tight steel structure. And this was respectively modeled and coordinated very tightly with it, right? So it's still hasn't been built on site, but what we received was actually 3D scan of the steel structure, which indicated that one of the side triggers is slightly off. This was kind of reported, discovered, and then the actual interior contractors did the 3D scan, and which usually that would be a nightmare scenario, right? But here we managed to get the scan in. I'll just run a short video again because it's a lengthy process. But again, so this is the point cloud, which imported in CATIA, then quickly meshed. Of course, it's not a car design point cloud, it's much rougher, but sufficient. And then to make sure we run interference and clearance check, which immediately showed exactly where the clash is. So it's same app, right? No need to change apps and go to somewhere else and so forth. So this was on the fly, so to say, clash analysis, exactly where the clash is. And as the stair is a parametric model, was actually pretty easy because basically what we find out is just like a slowed rotational deviation on the bottom. So updating the set out updates the geometry, design geometry, and then when we run the clash check again, it's clear, no clash, right? So this was like fairly easy fix, right? You can see this is actually with the clearance to the actual scanned as built structure is just enough for the thickness of the solid surfacing. So yeah, that's more or less it for me.
Wow. I'd say that's a summary from my end. This is a really exceptional presentation on the intricacies of the model that you put together to both manage and guide the design process, but then also to coordinate and collaborate with the contractors, subcontractors, and manufacturers. This is an exceptional model and exceptional work. Honestly, bravo. This is really incredible.
Thank you.
And thank you so much for the intimate tour of the model as well. It's not very often that a designer like yourself will welcome us in to review your model like this. It's really, really exceptional work. You can tell that you're a master CATIA user with lots of experience, because the organization of the model is incredible. The control of the modeling technique is something that we can all strive for. So it's absolutely exceptional work.
Thank you. Well, it's the only way to build something like this in an efficient way, right?
No, I absolutely agree. Absolutely. And it shows, yes. And it shows with the example at the end with the stair, the benefits of building the parametric model in such a way that
absolutely, yes,
when you link all of the drivers together, if you need to make a change based on unforeseen site circumstances, that update happens in minutes versus days with exactly. Versus a manual modeling process. So honestly, well done. Unfortunately, we don't have time for questions. I don't even have a question, to be quite clear. it's super impressive work. The only question I could ask is how long have you been working on this project? It looks like you put a
Oh
lot of
well,
time
no,
into it. It's
yes. So basically, what is it? I mean, we won the competition. I think it was like 2017. And then design stage. So this, I think we went for tender. Actually, I can check, but I think we went for tender around 2018, probably. If
so it's a
I
solid year.
remember.
A solid year then, going from competition
Yes.
phase design to tender.
Yes. With even more, like a year and a half
Okay.
or so.
Okay.
So yes, I mean, so this was more or less, yeah, finalized at the time.
Excellent. Well, I can't thank you enough for the webinar. Again, I feel very privileged to have been able to sit here with you to walk through the model. This will go up on the internet. Anybody with questions, you're more than welcome to ask them on our swim community. We'll provide a link.
Yeah.
We'll provide a link to the swim community, and we'll be able to answer any more detailed questions there, any specific questions there. If you'd like to see more information about the finished product, because this building is nearing completion now, right? You can check out the link to the B1M video about this tower, the Henderson project, to get a cleaner look at the finished product and the beautiful, because the result of all of this work is an exceptionally beautiful building. So take 10 minutes out of your day, go check out the B1M video and post any questions on the swim community, where we'll be happy to respond with, or we'll have Kaloyan to respond to questions and provide maybe a bit more insight into this incredible project. Do you have anything else to add, Kaloyan?
No, not that I can think of. Sure.
Great.
Yeah.
Well, again, thank you very much. Exceptional work.
Thank you.
Privileged to have you with us, and we'll reconnect again online to respond to any questions. Thank you everybody for joining and for following along for this in-depth look into how CATIA was used in the design process of the Henderson project in Hong Kong by Zaha Hadid Architects. Thank you.